Hi, I'm Jesse St. Laurent with Simplivity. I'm the VP of Product Strategy, and thanks for joining us today. I'm going to do a little bit of an overview on the Simplivity architecture and specifically drill down into the power of the OmniStack accelerator, which is part of the innovation in our technology. We even brought a card for show and tell so we can check out what the actual device looks like. So we just jump straight into it. What Simplivity's done is really bring three interesting things to the market. The first is the data virtualization platform, and this is really the core of what we've built. This is starting from the first line of code and building our system to be able to process inline deduplication, compression, optimization that happens at the very time of inception. So before data is ever written to a device in the system, it's already been deduplicated, compressed, and optimized. So we went from day zero, from the very first line of code we wrote in our system. This was one of the core design principles of the underlying platform. The second aspect of the system is global unified management. So this is the ability to manage an entire federation from all through vCenter and abstract all of the VM-based policies away from the underlying infrastructure. So there's no dependencies on things like IP addresses, LUNs, shares, controllers, any of the traditional constructs. You don't even define policies that talk to OmniCubes. You define them in terms of data centers. So how often do I protect a VM? How long do I keep that backup for, and where do I send it? Whether it's San Francisco, Boston, London, doesn't matter. That way you can do an entire tech refresh of a data center without ever having to worry about managing any of the underlying configurations. No downtime, no reconfiguration of policies, no stopping your backups, no manual data migration. So a very simple operation, all managed through vCenter. And the third is hyperconvergence. So this is the ability to take all of the aspects of the data center, the servers, the storage, the backup to disk devices, the data protection software, all of those components, and really create a single shared resource pool, similar to what VMware did for the business applications, but do it for all the infrastructure applications within the environment as well. So today what I want to do is drill down into specifically the data virtualization platform, how that works, and why that's so unique. So if we take a Simplivity OmniCube and we drill down inside of that box, when you look inside it, it's the standard components you would expect inside of any system. It's got hard drives, flash, DRAM, CPUs. What's unique, though, is what we've created is this data virtualization platform, and specifically the OmniCube accelerator. So this is actually the card. This powers every single OmniCube system in the market. So it's a mix of technology. This is designed and architected by our hardware engineering team. And this contains FPGA, it contains some DRAM, some supercapacitors, and a whole lot of performance. And what this does is this allows us to provide the deduplication, compression, optimization, those technologies actually inline without a negative performance impact on your system. In fact, the net result is a positive performance impact on your system. Things get faster, not slower, because the data efficiency is processed before it ever hits a device in the system. There's a tremendous amount of resources required to deduplicate data, to compress data. And if you do this in traditional Intel CPUs, which you can certainly do, we run it in our lab that way, it certainly works, it consumes a huge amount of CPU to run these operations. And if you want to do them inline, it introduces an enormous amount of latency into the environment. That's what the OmniCube accelerator is designed to do. It's designed to take all of those high latency, high overhead operations and make them instantaneous so that it actually makes the system faster. So any system that doesn't offer hardware acceleration, the net result is it consumes a tremendous amount of CPU to add any of this type of functionality. If we put the OmniCube accelerator inside and we look inside the data virtualization platform, there's really two layers to that system. There's the top layer, which is the presentation layer. Effectively, this is the data store that VMware sees. This is the NFS share that's presented up to the environment. And this is where the VM actually shows up. If we look at within that, there's a second layer, which is really the data management layer. You see that underneath the presentation layer. And this is where we manage all of the data. This is where we track it all. This is where you see us do things like backups and data movement and things like that. So when a write happens in this environment, what we see is, let's say it's a SQL server on the left-hand side here. When we do a write from that system, it goes down, it's registered in the presentation layer. Obviously, VMware is running a virtual machine. You need to be able to see the VM as it's being, the VM needs to be able to see all its data, so it's registered within that layer of the system. The second place it shows up is within the data management layer, and this is really where we're tracking all of the data, not just presenting it. And then the last step is that data is actually written down, because it's unique in this case, it's written down to the hard drives in the system in a nice, clean, sequential stripe, and it's been compressed before it does that. So we minimize the IOPS within the system. If we run another piece of data, we'll see the same behavior, right? Unique data is automatically compressed, reducing the number of IOPS that are required to hit the disk within that system. Do one more of those, and now let's switch to what happens when you see a duplicate piece of information. The duplicate write comes into the environment. Before it ever hits the underlying media in the system, it's been deduplicated. So it never consumes an IOP on a hard drive. We'll come back and talk about that in a minute and about the unique value of that. But effectively, the hard drive IOPS are one of the most limiting factors in any system that's designed to serve primary storage. Because of that, eliminating the IOP before it actually happens is incredibly powerful. So that's eliminated, but it's tracked within the virtualization layer, the data management layer. Same thing happens for a second write. So if we pick this up and do it a little bit faster in this case, what we see is a tremendous amount of I/O coming down from the hosts. It's all hitting the data management layer. It's registered, the VMs see all the data, but it's eliminated before it actually hits the underlying storage in the system. So there's a tremendous efficiency that comes from the system, and that load is really being handled by the OmniStack accelerator, that card that we showed at the very beginning, allowing your Intel CPUs to be made available to run all of the business applications that you expect to run within your virtual environment. If we look in this example, there's 10 references of this purple data block, all referencing a single compressed element on disk. What that means is, in this case, we eliminated 9 IOPS from actually having to happen, so a huge benefit within the infrastructure. If we take another step and we roll this out to multiple sites, we talked about the idea of global unified management. Simplivity manages what we call a federation, and it manages it globally. So no matter how many sites you have, they all join this common federation and allow you to have common management through vCenter. So the client that the VMware administrator is already using to manage this can be used to manage not only the VMs, but all the movement of the data, backups of data, restoration of the data, movement to the cloud, all that's managed through this interface. So in this case, we'll show a couple different sites, San Francisco and New York. We're the data virtualization platform spanning these two sites. What happens in this case is we've got our data stored in hard drive, so the permanent data is all there. We've got it registered within the presentation layer, so the VM can see its data, and it's being tracked in the data management layer. So if we want to do something like take a clone or take a backup of a piece of data, let's take a backup, and we'll do a local backup within, in this case, the San Francisco data center. When we do that, what we get is another copy within the data management layer. It's not exposed to the presentation layer because it's not actually a running virtual machine. It's a backup of that data set. No I/O actually occurs in order to take that backup. So you effectively get an instantaneous full image backup of a virtual machine that's fully compressed and optimized, and it's being saved now within this system. So if we take that and we want to do now, instead of a local backup, we want to do a remote backup, the functionality works exactly the same way. We take a copy of the data in the data management layer, we move it to the New York data center. In this case, you can think of it as a chemical formula or a recipe. What's been sent is H2O from San Francisco to New York. New York says, you know what, I've already got hydrogen over here, but I need oxygen. So it communicates back to San Francisco. San Francisco sends the missing element, and that element is now restored in the repository on the New York side of the environment. So this is not a snapshotting system where we're comparing a most recent snapshot when every time we're moving deltas. This is an environment that's inherently deduplicated, compressed, and optimized so that there's no common snapshot required, there's no common components. It compares against that common repository of data, regardless of what VM or what it's associated with, which backup it's associated with. If we want to then take that backup and restore it, we can simply promote it up so that it's visible in the presentation layer. In this case, oops, sorry, I missed a step. That was copying the missing bits, the oxygen, I think in my previous example, to the New York data center. Now to present it up, we don't want to present the backup because that would take something which was saved as an immutable copy, something that we want to preserve and keep a retention period on. What we want to do is take a copy of that. Again, doesn't take any I/O to do that. And we then present it up through the presentation layer you can start that virtual machine and you're up and running on the other side. So there's no dependencies on strings of snapshots or promoting a snapshot from 7 a.m. this morning doesn't impact the 8 or the 9 or the 10. This is a standalone full image backup of a virtual machine that when you promote, you simply get another logical copy with no actual overhead in capacity, no I/O consumed, and you can start running a virtual machine. This whole system that we show with 2 sites can go actually across a global environment, be multiple sites, including the cloud. This is direct connectivity into an Amazon AWS environment where you can define backup policies that not only go to London or San Francisco or Sydney or Tokyo, but also go to Amazon East or Amazon West or some other data center within Amazon's infrastructure, so that you can define a policy still within vCenter to allow those backups to send directly to the cloud. Here's the image within vCenter. You can see here there's, on the lower left-hand side, 6 different data centers being managed here, all with a single interface that the VMware administrator uses. So if we drill down on that a little bit, the question is, why is data management, why is data efficiency actually important? And what's the underlying problem? So if we rewind the clock a little bit, back to say the early 2000s, when the original folks that did deduplication technology came to market, they were trying to solve a very specific problem. They were trying to solve a capacity problem. Can we squeeze a terabyte of data in a 100 gig drive? And they were trying to solve a throughput problem. And for backup, that's absolutely the right problem to solve. That's not the problem that we're trying to solve in a virtual environment, though. What we're trying to solve now is how do we manage the data more effectively, and specifically, how do we address the need for primary storage? So if we look at hard drives, what's happened over the last decade is they've gone from being, say, 36 gig, maybe 100 gig, depending on what type of drive you're talking about, to drives today that are 3 terabytes, 4 terabytes, depending on how far out you look, 6 terabyte drives. So there's been an enormous increase in the capacity of drives, but the drives effectively do the same number of IOPS that they did a decade ago. So the point of optimization needs to change. The number one priority now isn't the capacity of the drive, it's in fact the IOPS capability of that drive. It used to be that we had, if we think of it as a straw in a cup of water, that a decade ago we've now got a straw in a 55-gallon drum. So the problem isn't the size of the repository of data, it's in fact the size of the connection to be able to get to that data. The second priority is really WAN bandwidth. If we're protecting primary data between multiple sites, the speed with which we can get it from site to site and the amount of bandwidth consumed as we move that data around is really critical in terms of managing costs. Flash capacity matters, right? So flash is still expensive in terms of dollars per gigabyte. And for us, what that means is we're focused on the capacity savings that you can get within flash to be able to make that, that component of the system as efficient as possible. And then hard drive capacity matters as well, but it's just not the number one priority. If we could find an efficient way to solve 1 through 3 and not worry about 4, we didn't worry so much about 4. So data efficiency is a fundamental requirement moving forward in these environments, right? DR is a requirement. Global data centers are becoming prevalent. Movement back and forth to the cloud is becoming more and more critical. So what does that mean? It means deduplication, compression, the ability to save costs, to enable DR, to be able to have all of the things that we've been talking about in terms of flexibility. The question is, how do you address these problems? You have to optimize for latency and for IOPS. You have to do it at a fine-grained level, and it has to be once and forever. So not process it when it goes over the WAN, and not process it once when it goes into the backup system, and once when it goes into an archive system, and again if it moves to the cloud, and again if it comes back from the cloud, and again when you write it to tape. There's too many points within the environment that you're investing resources, most of the time CPU, in order to make the data efficient. If you do it once, and you keep it in that efficient format its entire life, you now have a far more efficient system. You've not reprocessed the same data again and again and again. If we look at deduplication specifically, all dedupe methods have to do a couple of things. You have to analyze all the new data that comes into a system. You have to compare it to all the existing data and figure out, is it actually unique within this environment? You have to be able to find and eliminate those redundant pieces. So there's a bunch of decisions, and different technologies actually take very different approaches. You can approach this as a core part of your architecture, or you can try and add this into the system afterwards. You can approach it as an inline process, something that happens as the data is being written, or we can approach it as a post-processing exercise. You can do it for just one aspect of the system. You know, maybe you just do it for DRAM caching, or you just do it for some other aspect. Or you can do it on all tiers of media. You can do it for just one stage of the data, right? Maybe it's just when it goes to backup, that's the only time you're concerned about it. You can do partial or complete. Maybe it's only for a subset of the data, maybe it's for all the data. So if we take this to the logical, then there's really only one set of logical choices here. It's not an architectural decision versus an add-on. The right way to do this is systemically make it part of the architecture. From the time the first line of code is written, it has to be designed into the environment. Trying to take an existing file system or object store or distributed data store or whatever words we use to describe the data management layer of a system, and unwinding it enough to put deduplication, compression, these types of technologies in, and then putting it back together just isn't practical. The analogy I always use is it's like baking a cake. You take the cake out of the oven, you set it on the counter, you realize you left an egg on the counter that was supposed to be in the cake. There's no way that you can take that egg and put it in the cake and have someone eat it. I know I have a 7-year-old. We tried this exercise. There's no way you can get her to eat the cake after you've put that egg in it. Luckily, I thought ahead and saved a piece of the cake before I tried this exercise with my 7-year-old, so I was not the world's worst dad for destroying a cake. But the point here is you can't put it in the freezer and have it turn back into batter so you can mix the egg in. You made those decisions day one. It's now been many months or years worth of development. There's no going back. Inline or post-process, inline is the right answer to this problem. You want to eliminate the IOPS before they actually happen in your environment. You don't want to make a decision about, is this only for DRAM, is this only for flash, is this only for my capacity tier, is it only for archive? You just want it to happen once and impact every tier of the environment. Whether it's primary, backup, archive, if it's built into the underlying system, it's not a question of whether you do it for some VMs or all your VMs, you just do it for everything. The only reason not to do it for everything is if you don't have one of these that makes everything go a whole lot faster. If there's a significant performance impact, then there's a decision to be made. Do you do it for a small amount of the environment, or you do it for everything? If there's no performance impact, or even more powerful, if it makes things faster, the logical thing to do is to do it for everything. So no selective or automatic. It should be automatic. Everything globally, reads, writes, just do it once and keep it in that efficient format forever. So let's drill down one more layer into the Simplivity environment. The question is, what does this look like within our system? So this is a slide that's not typically an external slide for us, but we'll show it off a bit anyway. So we have an OmniCube system here. You see the OmniCube virtual controller. That's a piece of our intellectual property. That's a virtual machine running on top of ESXi. You see that there's also, within that environment, the OmniStack accelerator. So these two components are what we refer to as OmniStack. One of the things you saw this week is we announced OmniStack for a Cisco C240 platform. This drawing could be applicable whether it's the Cisco offering or the Simplivity OmniCube offering. The core technology is the same. When a write comes in from a virtual machine, it goes through this process, gets deduplicated, compressed, and optimized, and is written out to hard drives in the system. So if we zoom out a little bit and we look at two systems, we believe that data protection is the #1 priority of any system that's storing and protecting primary data. There's nothing more important than protecting the data. That means things like dual disk failures need to be protected from. If you have a node offline and you lose another drive in the system, you shouldn't lose data in that scenario. You need to be able to tolerate failures within your environment because failures will occur. It's the nature of IT infrastructure. It's not a question of if there will be a failure, it's a question of when there will be a failure. So the system needs to be designed to handle that. What we do is we protect the data locally within a given OmniCube. So in this case, the system on the left-hand side, when a write comes in and it's committed on that side, it's fully protected within that cube from an SSD failure, from the failure of an OmniCube accelerator, from the failure of the virtual controller itself, from the failure of any component in that system, the hard drives. There's data redundancy within that system. But to protect from a scenario where you have an entire node failure, somebody ceiling tile comes in, we have a leak in the data center. We've all seen scenarios where the water comes from the bottom up, the top down, where systems in the data center have failures. In this case, what we do, when that write comes in from a virtual machine into a vDisk, it's passed up to our virtual controller. We send it two separate places. We send it to the remote OmniCube. We send it to the local OmniCube. Specifically, the write is committed into the OmniCube accelerator. The card has RAM on the system. It's protected from power failures so that in the event of a power failure, the supercapacitors on the system actually commit that data onto the card, so it's there when power comes back to the system. Once it's acknowledged from those two cards, we then acknowledge back to VMware and it acknowledges back to your host. This all happens extremely quickly. And the underlying objective here is to be able to provide fast performance for production applications, integrated into the total solution offering that we've been talking about in terms of overall efficiency. So this is the Simplivity OmniCube technology, specifically talking a bit about our virtual controller, how the write path works within our environment, and how deduplication and compression optimization, when you accelerate them, and when you offload that burden from the Intel CPUs in the system, allow you to actually make your system faster rather than slower. Oops. So my name is Jesse St. Laurent. Thanks everyone for tuning in. This has been vBrownBag at VMworld 2014. Thanks a lot.